moving on. Sweet, slides work. Who am I? As I said, I'm Drew Hamilton. I worked for nearly 2 decades in higher ed, started at desktop support, ended up in Linux and network administration. About 4 years ago, I moved out of that industry and moved into cybersecurity, started at Asterisk Information Security as a security consultant, then went to CyberCX, actually finished up at CyberCX on Friday, and in a week's time, I am moving to Bunnings, where I'll be doing internal penetration testing for the corporation. Yeah, thank you. I'm looking forward to it. Can't wait to get my apron. As you can tell by now probably, I'm not a native Australian. I am originally from the United States. I was born and raised in North Carolina, but I came out here in early 2001, and I've been here ever since. Outside of working with computers, I'm very into high-powered rocketry, as you can see from the photos here. The photo on the left is what was my level 3 flight, which basically gave me the highest level certification in like hobby high-powered rocketry you can get. The photo on the right is a rocket that I flew out in the middle of nowhere in Queensland. I designed and fabricated that rocket myself by the nose cone, and it went to about 8.2 kilometers up and hit about Mach 2.6 before the motor stopped burning. Moving forward, why did I get into SDR? Well, basically, COVID happened, and we couldn't really fly rockets anymore. We couldn't get insurance because insurance organizations are a bit of a challenge these days post the fires over East and COVID. And other complications as well. So long story short, I was looking for a new hobby to pick up in the COVID world that I would be able to do from home fairly easily. And on March 2021, I was flicking through Twitter, and I happened to see a video like this on my Twitter feed. And that's obviously a Falcon 9 telemetry video from the second stage of a Falcon 9 rocket. But the thing that struck me about that video is there's no SpaceX branding or overlay on that image. This video was actually captured by amateur radio enthusiasts using SDRs and using an SDR and a Wi-Fi antenna. So if you look at the photo on the right, you can see a grid antenna. It's got what's known as an MMDS down converter attached to it because most rocket video, or I should say rocket telemetry and video downlink is in the S-band range. Once I saw this, I realized, hey, I can find a Wi-Fi antenna. I have an old laptop. I can get an SDR. Why don't I try to do this? Unfortunately, pretty quickly, once this stuff hit the public airways, SpaceX turned on the encrypt downlink button on their commercial hardware that they had the whole time. They had just not turned it on. So I will not be able to get unencrypted video telemetry from a SpaceX rocket. Electron and Rocket Lab out of New Zealand, they're a little more professional. They turn theirs on from the get-go. So you can definitely downlink the video telemetry from these vehicles. It's just unfortunately now it's all encrypted, so it's a little bit more challenging is probably what I would say. So moving ahead, where do we start? Basically, I'd probably like to just jump in with the quick legal disclaimer and also say, first and foremost, I'm not a lawyer. But that being said, there are a lot of things that you can pick up from your house with nothing more than an RTL SDR and a very rubbish new ELEC antenna. There are a lot of transmissions going on locally here in Perth that are completely unencrypted and very strong. In the top left, you can see a little packet in a waterfall from a screenshot I took. That's an APRS packet. Here in Australia, there's an entire frequency dedicated across the country for APRS. Had a bit of a meltdown publicly about how, we didn't even realize pagers still exist. They still exist today. They're still in use right now as we're talking. Don't publish that stuff, but have a look. It's pretty wild. Bottom left, this is a tool called RTL 433. You basically just run that command out, and chances are good somebody within your immediate vicinity is running a wireless weather station. Why go out and buy a multi-$100 lacrosse system when you can just listen to your next door neighbors, right? So already just sitting at your house, there are plenty of things that you can do on the ground to listen in. There's a lot of narrow FM around town as well. Trans Perth got handed the Waypole handhelds after Waypole got their P25 system installed, which is encrypted, which is good. We should obviously, ideally, not be able to listen to the cops when they're doing things. But yeah, now all of their radios are with Trans Perth, and they're obviously all in the clear. So if you ever want to listen to Perth Underground on a Saturday night, it's an eye-opener. Moving on from that, though, because I'm going to be honest, this stuff, while I find it immensely interesting, isn't really what I wanted to talk to you guys about. I want to talk to you about satellite amateur radio with SDRs. So, as part of this hobby, over time, I've come to realize that there are a lot of people around the world that are using software-defined radios to basically receive weather satellite imagery in real time from either polar orbiting low Earth orbit satellites or geostationary satellites. Basically, it's a very wide-ranging sort of topic to look into, and there's a lot of things that you can do. But for the start, most people start with NOAA APT. It's called APT, it's called Automatic Picture Transmission. It's black and white, as you can see from this image up here on the right-hand side. On the left-hand side, you get infrared visible band. This is an analog transmission that comes down over the 2-meter band, roughly 137 megahertz in frequency. The bandwidth roughly 34 kilohertz wide. Normally your best bet is to set a wider sample rate so you don't have to move and track the satellite as it's passing, because as you'll realize with polar orbiting satellites, you deal with a Doppler shift as the satellite crosses over the sky. So either you can lock onto the carrier of the transmission and try to track it manually or via software, or you can just open up and listen to a bit more of the downlink and effectively mitigate that issue. These signals are very easy to get. If you had a handheld transceiver like a Baofeng or a Yaesu or anything like that, you could tune into this frequency, look on software package like, say, gPredict, Orbitron. On Android, there's a program called Look for Sat. Find a pass of NOAA 15, 18, or 19 and go outside, and you'll hear these signals. It sounds like really bad sort of like electronic dance music, but it carries quite a bit of data. As I said, they're very easily received and decoded. I've used an RTL SDR that I've got in the corner, one of these right here, to do this in the past. For most of the stuff, when I was doing 2-meter reception, though, I was using an AirSpy Mini, which is a slightly better SDR. So you have multiple antennas that you can use to track these satellites as they're passing overhead and downlinking information. You can use a Yagi antenna. That's an Aero satellite antenna there on the screen. You only use the 2-meter band of that Yagi. That's actually designed to do ISS conversations with other people, which is another thing that more ham radio enthusiasts do instead of software-defined radio, but it's an option. Another thing you can make is basically a V-dipole, which is this image here, which is nothing but rabbit ear antennas from an old television set. You open that thing up to 120 degrees, extend the elements out to the appropriate length of, roughly 53 centimeters, and you'll be able to pick up that imagery. A lot of people build stations to basically automatically capture all of these passes and then process the imagery after the fact. And QFH enjoy it, but still we have PT or low rate picture transmission. So Meteor M2-1, 2-2, which was the second satellite of where these images came from. Unfortunately, off on that satellite. Russian satellites are interesting. It's probably the simplest way I can say it. They're not very reliable. They've recently launched Meteor M2-3, which is also doing low-rate picture transmission. Unfortunately, most people that have looked at it in the community over the past 6 to 8 weeks, or 4 to 6 weeks, have realized that most likely the QFH antenna that's on the satellite, similar to the antenna I showed in the prior screen, but that's what they have on board on the actual Meteor satellite on orbit to transmit, it did not fully deploy. So people are noticing weird things where about halfway through the pass, their signal to noise ratio will drop through the floor with standard like QFH omnidirectional antennas. So if you want to have a look at low rate picture transmission, I would recommend grabbing a 3-element 2-meter Yagi or bigger, and then actually hand tracking that as it goes past. That'll give you your best chance of success. So on this screen, I want to call out as well, up in the top left, there's a screenshot of a tool called SatDump. SatDump is pretty much the sole tool I use to download weather satellite imagery. It is developed by a bunch of European teenagers primarily, it seems, who are exceptionally smart people, and I am very happy that I've come across the software stack. As you can see from the screen, I'll give you a bit of a rundown. So you can see how you've got a constellation there with 4 distinct constellations within that. So that's a sign that this transmission is quadrangular phase shift keying. So basically it's got 4 constellation points in the transmission. The better your signal to noise ratio, the clearer and more separated that constellation will become when you're receiving the imagery. So LRPT is fun. Sadly, there's only one satellite that's doing it right now because it's in polar orbit. At best, you get 2 attempts per day. One of them will be at night, and because there's so little bandwidth for this satellite in the pastime, effectively it only spits out a RGB JPEG, so at night your image will be completely black. Interesting, but yeah, not something that you want to spend that much time on just for the hassle of like getting out there and finding the satellite alone. So moving forward, let's bump it up a notch. Instead of sitting on 2 meter, let's go to L-band. So in the L-band, there are a lot of polar orbiting weather satellites that transmit weather imagery and other sensor data down on L-band. These images are often much better in terms of the resolution than the low-rate picture transmission. Definitely heaps better than the automated picture transmission, APT of the NOAA birds. And as you can see here on the left, obviously this satellite status spreadsheet or list is a bit out of date, but all of the NOAA 15, 18, and 19 polar orbiting birds have HRPT transmitters. METOP A, sadly, has turned off now. METOP B and C is still on. The Finyoung FY3 series is available for some people around the world. China, for whatever reason, has decided to turn off all their polar orbiting satellites over Australia. So I've never been able to get a Finyoung image, which is a bit disappointing, but it's okay. We also have Meteor in 2-2 and now in 2-3 that just recently launched, as I mentioned. So when you're doing L-band satellite reception, you effectively need more gain, which requires a bigger dish and a better feed to receive that, and quite often a low noise amplifier as well. So I'm going to step over here real quick and just show you. This is a, cool, thank you, I should have done that. This is a 3D printed helix for L-band that I made in my shed. I've got a mate who has a 3D printer. He can spit out these scaffolds in next to no time. It's a design from a guy named Derek SGC, or at least that's what he goes online as on Twitter and YouTube. Czech Republic guy, I believe. Really helpful, really friendly. As you can tell, this feed is a helix, so it's circular polarized, and this feed is a left-hand circular polarization feed, which basically means when you're holding what you're wrapping the coil against, you're holding it, well, you're holding what you're wrapping against with your right hand, and you're wrapping with your left hand, hence the left-hand circular polarization. So that is a 1.7 gigahertz feed for L-band transmissions. This is a right-hand circularized feed for S-band transmissions, which is a higher frequency range, roughly 2.1 to 2.3 gigahertz. So as you can see, when compared to the L-band feed, the S-band feed is tighter in terms of diameter of the helix. So the helix that you wrap the diameter of that helix, as well as the spacing between the elements, is all that effectively tunes this feed to be able to receive these satellite transmissions. I know this probably looks a bit complex, but it's literally just a 3D printed scaffold with some copper that I wrapped by hand on a glass. So, as I said, the generic RTL SDR, you can even get net up, even though, as you can see, the data rate is roughly 4.2 million bits per second. These SDRs only do about 3 million samples per second, so it's a little bit underbaked for doing net up, but it can still be done. I mentioned on the bottom right, what you would probably all recognize as a foxtail dish. I pick these things up off the side of the road when people are doing birdside collection, because everybody has been throwing them out because nobody uses foxtail satellite anymore. They work very well for L-band and S-band reception work. As you can see, I've got an AirSpy Mini, basically just Velcro to the arm of the dish. I've got a Sawbird connected directly to the feed that's bolted to the dish. And then I just run a USB extension lead from the software-defined radio into a laptop. That is literally as simple of a setup as you need to get up and running on these sorts of things. One thing I will mention, though, is that obviously hand tracking with a dish on a tripod can be challenging, especially when you go up with larger sized dishes. That being said, it's actually not that hard. L-band is quite forgiving, so just sort of wave the dish around and see, and quite often you'll be able to dial it in fairly quickly. So this is the current setup that I have now for L-band satellite reception. Obviously, you can see the dish is a little bit larger. That's a 90 centimeter offset. There's a crew up north of the river called Tritech that does satellite stuff. They will sell you one of those dishes for 82 Australian dollars. They've got a pallet of them. It comes in a kit, it is super cheap, and it is a phenomenal dish for the money for doing L-band stuff. You can get everything with that. One thing I will call out as well, you can see that the feed is the same one as the one I have here. The cabling from the low noise amplifier to my SDR I've swapped. So that's what's known as LMR 400. When you're up at higher frequency ranges, basically 1 gigahertz or above, cabling losses start to become a real issue. So if you can use LMR 400 instead of something like RG58, you'll get effectively a 1 dB SNR boost just from swapping that cable alone. And I mean, it doesn't matter how long it is. I can run 3 meters of LMR 400 to replace a 10 centimeter long piece of RG58. I still get that SNR boost. Obviously, if you're using a down converter, it's not that much of an issue. But for something like this, where I'm receiving it at 1.7 gigahertz, it actually makes a difference. And then obviously, that's the laptop I've got here. I've upgraded recently because I need a gruntier laptop. So because I wasn't here yesterday, because I've been quite sick for the second half of this week, I took the opportunity to go out in the driveway and get a couple of L-band images for you guys to show you basically yourself yesterday when you're here at the con, and then give you a bit of a compare and contrast. So we'll start over here with NOAA 19. This is an AVHRR image on the left. That's the advanced, very high resolution radiometer. It's basically 1 square kilometer per pixel. It has 3 visible bands, 2 infrared bands, and then you basically use that imagery to build out composite images based off of those base bands. So this image on the left is called a, let me just make sure, yeah, NOAA Natural Color Corrected. These are new composites that have only come out in SatDump recently. There's constant development going on in this space, both with composites, people finding channels and new things in data. It's a fast-moving space is the best way I can say it. On the top right, you've got what's known as the day microphysics corrected image. I say corrected because as these satellites are passing over the Earth, the curvature of the Earth comes into play. And so the images actually are sort of bent around the sides, so you use software processing to effectively flatten that out to make it look normal. And that's the reason why on either side of the images, the actual apparent resolution of the image degrades a bit when you've got a corrected image. I use SatDump as per usual with this. I put this in to show you that unlike the Meteor satellite, you can see that this only has 2 points in the constellation. That's because NOAA transmits binary phase shift keying instead of quadranture. There's no forward error correction on these transmissions. They're great, but at the same time, they could be better if it was quadranture, if there was error correction enabled, that sort of thing. And you can see there, I had a good signal to noise ratio, roughly 16 dB on that pass, but also at the top of the image, you can see where I didn't have proper sync before it finally clicked in. And then also in the day physics image, you can see a line through there, which is basically right where I didn't have good alignment and I lost some data. So NOAA 19, NOAA 18, NOAA 15, they all have the AVHRR imager on them. They are degrading because they're a bit old. And I wanted to do NOAA 19 as well, because this is the same satellite from the first image of the presentation that fell over. They spent a lot of money to repair it and then launched it, and it's still in use today. But it just goes to show that even if you drop a satellite and have to spend hundreds of millions of dollars, you can still get it back in workable condition. Conversely, this is a METOP-B AHRPT image. This is the exact same imager, the AVHRR imager, that the NOAA fleet uses, the NOAA POSE fleet. Granted, it is a slightly newer imager. That being said, it has FEC. It's a quadranture phase shift keying transmission. So you get a lot less noise from the image. You get a lot more error correction. If I zoomed in on the image, I wouldn't have individual dots where I just had white pixels where I missed a bit of data. They're very very good. I like, out of all the L-band polar birds, I find METOP the easiest to receive, and it produces the best pictures, in my opinion. It also has more instruments. So up in the top right, you have what's known as an IASI image. That doesn't look like much to me. It's definitely not as pretty as the color composites. But apparently, this one instrument has effectively doubled the numeric weather prediction capability of humans. They're arguably 50 to 60% of the reason why we now have 10-day weather forecasts instead of 7-day weather forecasts. So this one instrument measures temperature and humidity in the atmosphere at 1 kilometer bands. So it allows, when you take all that data along with all the other weather data that meteorologists have, when they plumb that into very big computers, this is what allows us to give like proper weather predictions for a longer period of time. And I think one of the things that I find really curious about it is they didn't know when they launched these instruments just how impactful it would be until they started crunching the data. So it's one of those things where, from my perspective, these technologies are still advancing, and we're still learning new things about the weather and that sort of stuff. So really strong transmissions with METOP. I do the sampling at 6 million samples per second because, as I showed in the earlier slide, the transmission's roughly 4.2 megabit per second. But yeah, it's a wonderful satellite, both METOP B and C. So moving past that, well, let's say we don't want to look at polar orbiting satellites anymore. Let's go up to geostationary satellites. So geostationary is interesting because you can easily receive full disk imagery of the entire planet from the perspective of that geostationary weather satellite. The downside is they're roughly 36,000 kilometers away from us in geostationary orbit. The upside is they don't move because they're geostationary, so you just align your dish and get it all nice and dialed in. Long hair, don't care, off you go. You know, it's great stuff. So originally, obviously, I started with polar orbiting satellites. I've shifted over to geostationary quite heavily just because of the data and the simplicity. In this image up here on the top left, this is from usradioguy.com. This is a scale image with Earth and all the polar orbiting satellite stuff basically smashed on right at the very left-hand side of that image in front of Earth. So that's where all the satellites from the previous imagery I was showing are located roughly. On the right-hand side is geostationary orbit. And then in the middle is basically GPS. So you can kind of tell that that's a true-to-scale distance image, how far away these things are. But like I said, they're not moving from the apparent perspective of us on the ground, so they're very easy to target with an appropriate dish. On the bottom right, you can see I've got a Foxtel dish on a tripod I found on the side of the road, and an old ThinkPad laptop, and this was me successfully receiving what's known as GK2A, GeoComSat 2A, which is a South Korean geostationary weather satellite. So popping over here, this is what you can expect to get from GK2A. It's got a transmission called Low Rate Information Transmission, or LRIT. It's roughly 64 kilobits per second, binary phase shift keying. Every 10 minutes, you get a single IR 105 image, infrared image. But because you get them every 10 minutes, you can make very detailed GIFs out of those images because you get 144 of them per day. But not only can you process them in that way to make animations of the planet, you can then post-process the images. So on the left-hand side, this is a tool known as Sanchez, which is used to false color images. It's the same color palette that people use for the APT transmissions from NOAA to false colorize those images if they want to. On the right hand, we have an image that's gone through IR enhancement process. So you can actually run a Python script over the images that come out from the satellite, and it will effectively use IR enhancements to show you weather strength in real time off that image. So moving forward from that, you can then take that stuff and obviously animate it again. So GK2A is neat. I like it, but from my perspective, it's probably the most useful scientific geostationary satellite we can see here in Australia, but at the same time, it's the most underwhelming because it's only infrared. So moving past that, I'd like to show you Electro L3 LRIT. So Electro L3 is a Russian geostationary weather satellite. It sits roughly 30 degrees elevation from us over the equator, roughly south of the tip of India. So I can just see this satellite from my backyard with a 85 centimeter offset. It transmits every 3 hours, except for in the middle of the day when it would transmit a fully illuminated full disk image. I don't know why the Russians turn it off for that time slot. It just, yeah, it's frustrating. It would be a lot better if they gave you a full disk image, especially when they commission the things, they always drop 1 or 2 out just to show everybody it can be done, and then promptly don't transmit for that session. So it does 3 visible bands and then 2 infrared bands. So you get basically a channels 1, 2, 3, and then infrared's channels 9 and 10 every 3 hours. So what I've done is taken some natural color composites, which come from the 3 visible images, and you can see the progression from a single day, from the start to the end of the day, from our perspective, from this satellite, and then the infrared 9 and 10 images. I've had a station running on Electro L3 since roughly April of 2022. I consume these images daily. I like them a lot, even though, as you can see, especially like say in that second image, the composites that come down from the satellite are all, well, they're converted into JPEG, as are the original bands that are transmitted. They are overexposed images, so where parts of the Earth that are highly illuminated, you'll get washed out imagery. But still, it's color, it's natural color composites. I enjoy electro satellite images. Moving past that, there's also a Chinese geostationary satellite network called Fingyang 2. These are images from Fingyang 2G. This is not low rate information transmission. This is a bucket load of data. A single fully illuminated false color image like that, that's a crop, by the way, because when I tried to put the real image in my presentation, it crashed my presentation software. They're roughly 90 megabyte images. This satellite transmits hourly at the top of the hour. It does include here, and then multiple infrared bands and also a water vapor band. So not only does it do hourly transmissions, it also does 4 times a day a half-hourly transmission as well. I'm not sure the reasoning for that, other than maybe they wanted to get the fully illuminated full disk image of the planet daily, because it does happen to coincide with one of the fully illuminated time slots. But yeah, this is a really interesting satellite. It's a linear transmitter, which most geostationary satellites, bar the electro satellite I showed on the last slide, which is a circular polarized transmission, you're better off using linear feeds and prime dishes to receive these types of signals. So now that I've shown you this, I want to quickly go to the next slide, which is a screen recording of SatDump as Fingyang 2G is just starting up to transmit at the top of the hour time slot. The reason why I wanted to show you this is because I've shown you screenshots of SatDump, but I haven't actually shown you any video of what it looks like. This satellite is spin stabilized at 100 revolutions per minute. So if I had to guess, I would think that's the reason why the signal looks the way it does. But to be honest with you, even I don't know. So this is basically what it does at the start of the transmission. This is probably a minute or so before it starts actually transmitting the imagery. So you can see down on the binary phase shifting demodulator on the left-hand side, it's having a bit of a drama because it's like, I don't know what's going on here. I've got a massive carrier spike up top. I've got good SNR, but the constellation isn't locking, right? On the bottom-hand side, you've got your image progress as the image is decrypting, or sorry, as the image is receiving. This is what's known as live processing. When I look at satellites, if you have a computer that's grunty enough to handle it, turning on live processing helps a lot, at least for me, primarily because on the bottom left, the average SNR and the SNR figures help you align things immensely. If you're just looking at the signal from the waterfall and the FFT above and trying to ascertain what's going on, and there we go, my converted video dies there. But basically you can see just there, that's when it was just starting to spin up and transmitting the image. So moving forward from Pingyang 2, we now have FY4. FY4A and FY4B are on orbit now. They're Chinese geostationary weather satellites as well. When FY4A started up, I got really excited because it was going to be another low-rate information transmission, or LRIT bird, hourly transmissions, full disk imagery. I was like, oh, sweet, you know, like I'm going to have something else to point at and some new data to start collecting. It's abysmal. It's the best way I can say that image on the left is like 4-bit resolution. You zoom into that, it is just woefully inadequate for anything. It's the worst geostationary data I've ever received, and it is the newest geostationary satellite constellation that I point at. I don't know what's going on with China, but yeah, it's confusing to me. They also do a vapor band and then an infrared band. I lost a bit of the last lines of that vapor band transmission. This thing's a little bit hard to receive if you're not using linear feeds and linear dishes. Going past that, I know I said Pingyang 4A was bad. Well, let's have a look at Pingyang 4B. On the top right is a Pingyang 4B transmission with the stereotypical LRIT hump that you would expect to see. On the left is Pingyang 4A, where I'm successfully live decoding as it's transmitting. One of the things you'll notice between left and right is on the right, you have all that other transmission on the background. What that is the original satellite I showed you, GK2A. That's its high rate information transmission signal. You're probably thinking, well, that's a bit of a problem because you don't really want one satellite's transmission behind another satellite's transmission at the same time if you want to decode either one of them successfully. This is a headache. I don't know why they chose to basically set their low rate information transmission frequency to stomp on an already established frequency for a satellite that effectively sits beside it in geo orbit. And yet here we are. So the last time I had looked at that, when it was still doing the normal transmissions, they had dropped the power rate down for the LRIT transmitter, I assume, to try to sort of help with this issue. But recently, the Chinese Meteorological Association, or whatever they're called technically, have moved into what's known as intensified operations with FY4B. I happened to have a look at it, and these bottom two images are transmissions from that intensified operation. That's not LRIT, that's binary phase shift keying. It's massively wider than what it would normally transmit across, as you can see from this image versus this image, and you can see the GK2A transmission on the background on the top and bottom of each one of these. I have no idea what China is doing with the FY4 constellation. I'm going to try to have a look at their high rate information transmission, which is more channels, better imagery than the LRIT that they do. I'm probably a week or so from looking at that. I've just got to build myself a linear Cantana feed. But yeah, so you can look at things and find weird things in space, and then you talk to people on Twitter and they're like, yeah, I'm seeing this weird stuff too, and this website says this. It's a really interesting sort of space to be in right now. So moving on, stations. I'm currently running 3 stations. On the left is GK2A, on the right of that is my Electro L3 station, and then an FY2G station. These things run 24/7 in my backyard. I'm consuming a lot of data at the moment. I've got roughly half a terabyte of geostationary satellite imagery so far. And because I'm sitting on GK2A, I've only been listening, or sorry, FY2G, I've only been listening to that satellite since sort of late January. I've probably got 400 gig of data from it alone because of just how large the images are and how often it transmits. So moving forward, where do we go from here? Well, we need bigger dishes, we need more power, we need to get better images, right? So I found this dish off Gumtree from a guy north of the river for $120. He threw the base in for me for an extra $10. It's a 1.2 meter offset. It's phenomenal for doing bigger things, be it L-band, S-band, or even X-band. So moving forward, I've been able to use that dish to get Electro L3 HRIT, which is similar to the LRIT transmission I was speaking to earlier. This starts at the 12th of the hour instead of the 42nd of the hour. Every 3 hours, it does channels 1 through 10 from the Electro satellite. So the only thing that I could do better from an Electro geostationary satellite perspective is if I started pulling down the raw X-band downlink data as opposed to this high rate information transmission. As you can see in SatDump, it looks quite a bit different in terms of the transmission. That's how HRIT looks. You don't need that much SNR to actually get lock into code. I had a little over 4 there, and that worked great. And then, yeah, so that's a visible band natural color composite, and then some of the other different bands that you get, be it infrared or water vapor. Moving on from there, stepping up to S-band. So S-band is similar to L-band, but obviously it's higher in frequency, so roughly 2.1 2.1 to 2.3 gigahertz. Obviously, that's starting to get very close to 2.4 gigahertz Wi-Fi, which is an absolute nightmare for RF interference perspective. So my setup for this is a little bit different. Same Foxtel dish, smaller feed. I've got a mini circuits LNA, which costs more but is better, and it's an S-band capable LNA. And then I have what's known as a cavity filter. So that cavity filter basically filters out everything bar the S-band signals that I'm actually looking for. So it's got a hard cutoff at 2300. Anything above that in Wi-Fi, it just completely filters out. So when it comes to S-band, top right, NOAA, all the 3 NOAA satellites are now doing S-band HRPT just like they do on L-band. So that's an example of that. On the bottom right, this is Coriolis. That's a United States Department of Defense weather satellite to do wind measurements for the United States Navy. So apparently if you're in the US Navy on a boat, you point at this satellite and it tells you how windy things are going to be around you and everywhere else. It's been up for a long time. It was a technological demonstrator. It's unencrypted. I'm not going to go to jail for looking at that. But yeah, it's reasonably interesting. That being said, there's not much weather imagery on S-band in general. So whilst it's good to have the capability to look at S-band, from a pretty picture perspective, it's not the greatest place to be. So just wanted to show a few favorite pictures that I've been able to get over time. So this is an Electro L3 natural color composite from the April the 20th, 2023 solar eclipse that happened here in Australia. So the satellite took this photo at 11:30 a.m., which was when Exmouth was in totality for roughly 1 to 2 minutes. So it was just a weird stroke of luck that the satellite took the photo at the exact same time that we were under a solar eclipse. So it took the photo at 11:30, transmitted it down at 11:42. I was working from home that day, so about 7-8 minutes later, after that transmission finished, I immediately dumped out and decoded the imagery because I wanted to look at the eclipse. So I thought that was pretty interesting. Right here, this is a METOP-B AHRPT image that is 4,028 lines in total length. I got this image from taking that dish I showed earlier, the 90 centimeter offset, putting it in the back of my car and driving up to the local, my son's school oval.
I live in the hills, on the side of the hill, surrounded by trees. I do not have good line of sight from horizon to do polar observations. So you can take your stuff on the road. It's a hassle, it's a headache, but you learn new things like, peg things down when the wind's blowing, because the wind never blows on your property. But if you're out on the coastline and trying to do a demonstration for a bunch of school students, you'll break your feed and disappoint everyone. Don't do that. But yeah, so if you were in a clear location with like clear line of sight to either side of the horizon, you can get near 5,000 lines from an image. It's not unreasonable to expect for us to be able to see Indonesia from these satellite images as they pass by. So moving forward, X-band. I've been on L-band for a while. I've done a bit of S-band. I'm now probably days away from starting to test on X-band. X-band is expensive. There's a lot to do there. All of the satellites that I've basically shown you thus far have downlinks for except for the NOAA pose, but have X-band downlinks where you can get raw data from the satellite. The X-band transmissions will not be usable for something like a HAC RF unless you're doing HAC or maybe Terra. Everything else is going to be 30 to 50 million samples per second or more base requirement. So I bought a Blade RF micro. It's got an FPGA on board. It's stupidly expensive. If anybody wants to do some 3G, 4G testing, we can use that. But yeah, it's a very expensive SDR, but it's very good because it can do up to 60 million samples per second. They just released a firmware in February to where you can go from 12-bit to 8-bit and unlock 122 million samples per second. Sky's a bit of the limit. X-band sits at around the high 7s to maybe 8.4 gigahertz in frequency range. The SDR that I bought only goes up to 6 gigahertz, so I need a down converter. So basically what that thing does is takes X-band signals and then downshifts them to a lower frequency that I can then tune in with my SDR to receive. So it's not as expensive as the Blade RF that costs $540 US, but a couple €100 minimum, and I bought it from a guy off Twitter. On the bottom right is a Mitech low noise amplifier for X-band. I got lucky with this. I found it on eBay. It was secondhand. They had only shipped to the States. Luckily, I have a workaround with that given my accent. So I bought that thing. So I have all the hardware in hand. I've got connectors on the way that are low loss connectors. X-band looks to be fun. It's a lot more challenging as well. Hand tracking with that 1.2 centimeter off or 1.2 meter offset I showed earlier for a satellite in polar orbit is going to be hard. X-band is even harder in terms of like your margin for error for the tracking. It's going to be a nightmare, and I'm very much looking forward to it. So that being said, that's pretty much it for my presentation. But I'd like to open it up to questions. I know this stuff is not very prevalent, so if anybody wants to ask anything, I'd love to hear it. Yes, please. Oh, thank you.
I noticed that you're doing listening device.
Yes. Uh-huh. Yes. Yeah, no, that's a very good question. What I'm doing is all non-PII. I showed you the POXEG pager stuff earlier. Yeah, don't retransmit that. It's sort of accepted in most circles that if you're just listening and not using the information, you're probably not going to get into trouble, because how is anybody going to know? All these SDRs, all of these SDRs, bar this HackRF, are receive only. The HackRF has very, very low transmit capabilities. So you're not going to run into issues with like basically stomping on somebody else's license spectrum and having an ACMA engineer come on site and threaten you with $10,000 fines. Yeah, they do that. But yeah, all of the satellite stuff that I'm doing, it's all designed to be publicly consumable by anyone in the world. The only satellite I showed that has any encryption whatsoever is actually the GK2A satellite, and the South Korean Meteorological Organization publishes the decryption key on their website in a sort of, here's a software package of how to look at our images. And so the way SatDup does it, because they were a little bit concerned about pre-baking that decryption key into the software because they thought, oh, this might actually be a little bit of a legal gray area. When you boot up and start listening to GK2A, you need an internet connection because your laptop will actually go out and fetch it from the website and then load it for you automatically. So I agree with you, especially with some of the more local things that we can listen to. Just because you can do it definitely does not mean it's legal. And you can definitely run into pretty severe headaches if you start taking stuff like that and plumbing it out into the outside world. No, because you're not transmitting. Basically, when you're doing amateur radio stuff, primarily the license is all around you transmitting on licensed spectrum. So this is why when you have a ham radio license, the restrictions around your license are based around what bands you can access and transmit on and what wattage that you can transmit across those bands. So because I'm not doing any transmission, I'm only doing reception, it's fine. I don't want to transmit to a satellite is probably what I can say as well. I'm very much happy to just listen and observe. Yeah, yes, sir.
Is there any header information or beacons that come from the satellites?
Heaps. Heaps.
Looking at, listening to?
Yeah, so most of the satellites, well, basically all the transmissions have preambles, they have sync codes, everything is different. And so, like, by understanding that stuff, you can actually sort of reverse engineer the signals. I've only started playing with stuff like that. There's a tool called Hobbits where I can basically take the CADU files I get from satellites, plumb that into Hobbits, and I can look at the bit stream. I can see like electro transmissions from multiple time slots, that sort of thing. I just see boxes at the moment though and patterns. There are people that can look at this stuff and tell you, hey, like that's unencrypted and like, yeah, we should look at that. It's just magic to me. But yeah, someday, hopefully. Do you mind, do we have time for a couple more? Yes, sir.
Yeah, so you talk about the challenges of manual tracking. Can you look at automating that?
Yes. To get a rotator that has the strength to hold the dishes I use and the resolution necessary to track satellites, especially on X-band, your mount's going to run 4 figures minimum, not including shipping. Nobody makes them here. So like I've looked into doing that. That's a very long down the track project. A lot of people make them manually, spend a lot of time on them with encoders and things of that nature. But for right now, I think I'm just going to stick to hand tracking because I just don't have the money. It's already expensive enough just buying all the other stuff without like going into a rotator. Look, I've got a couple of telescope mounts. I've thought about using one of them for a satellite. I've got an equatorial mount. By software, it is capable of being used with like gPredict or Orbitron to slew the telescope mount automatically, but I've not gone down that path yet. Ben, you had a question?
Yeah, since steganography is stable beams kind of took that lane, the rise of accessible SDRs kind of kept alive the kind of analog processing side of the CTFs. That said, are all these space agencies sitting on the capability for the world's greatest camera flight?
Well, yeah, that like my shirt. This is the Hackasat, competition that they do yearly. This year, I believe, was the first year where like the finalists of the Hackasat comp at DEF CON, I believe it was DEF CON or Black Hat 1, they actually got the ability to try to hack a satellite on orbit in real time. So I believe it was a CubeSat, but basically, like, yeah, there were, I think maybe 5 teams, like, who had access to the hardware and everything else, and got given the get out of jail free card to start transmitting to a satellite in real time to try to, I assume, make it do things, change its on orbit parameters, that sort of stuff. And DoD is starting to realize that, like, listening to the hacker community about all of the signals that they just blast across the world on a regular basis might help them in the long run. So I think they're trying to sort of rectify that now and build a sort of more less adversarial relationship. Yeah. No worries. Thank you, sir. Just one, oh yeah.
Yeah, probably time for one more.
One more. Go ahead, sir. Okay, so for all the L-band stuff that I do, basically max resolution is 1 square kilometer per pixel per visible per band, right? Some are a little bit less resolution, some are slightly higher resolution, like I believe the Fing Young visible imagery is probably 0.8, I think off the top of my head. That being said, X-band, with some of the satellites up there, you get 250 meters per pixel resolution. I was looking at some imagery from Aqua from a couple days ago from Southern Europe, and it's like you're sitting there looking at Sicily. There's Mount Etna. You can see the smoke coming out of it. The level of, like, apparent resolution you can get from X-band is really quite phenomenal, and that's the reason why I want to go there, and that's the reason why the transmissions are such a high or such a large sample width, because there's so much data that they're dumping down, which is also why they're on X, because there's not enough bandwidth in L or S bands to handle a 50 million sample per second transmission. Yeah. Okay.
Cool. Thanks again for joining us. Super the dog and coming in tonight. So really